All right. Well, good morning, afternoon, or evening to everybody who has joined thus far. Appreciate you being here for this webinar. My name is Brian Benish with DSIAC, and I'm glad to have everyone in attendance so far. I know there's a few folks still joining. So to kick this off, I will just give a quick introduction to the organization, DSIAC, give a little bit of a logistics overview of this AnyMeeting platform, and then kick the remainder of the time over to Ken and have the Q&A at the end. So quickly, as an introduction to the organization, DSIAC, we are the Defense Systems Information Analysis Center, DSIAC. We are a DoD entity under DTIC, the Defense Technical Information Center, which I typically explain as being the DoD's technical library, housing millions and millions of technical reports that were produced, at least in part, by DoD or federal funds. And so, DTIC being this huge technical library for the R&E, the DoD research engineering community, it can become somewhat challenging to navigate through. And so, DTIC has stood up these IACs, these Information Analysis Center. We are one of three of them, and our job is to help folks like many of you who are joining in on this webinar today, to help you find information that's out there in the larger research engineering community. So we have information researchers on staff, technical folks on staff, who kind of know the lay of the land, know who's who, and where work's being done. And so we want to help connect you with those individuals, help you get a head start on whatever work you're pursuing or conducting. And so one way we accomplish that is by conducting these webinars, hosting monthly webinars to create an awareness of work that is being done within the DoD research and engineering community, so that there, again, is that awareness, hopefully reducing some of the redundancy and duplication of efforts that inevitably will happen in the DoD. And then hopefully fostering some collaboration. Folks who maybe didn't know work was being done, they're doing some similar work, and there's a collaborative opportunity that comes of it. And so I'd encourage you, if you want to get some more information about DSIAC, just to simply go on our website, dsiac.org, poke around, see what you can find. And if you have any questions, you can email the contact alias or myself, Brian Benish, should be available somewhere online. I'd be happy to chat with you more about our organization. So that's a quick overview of us. In terms of logistics for the webinar, just first of all, for anybody who has joined in via phone, the slides are available for download on our website. So if you went to dsiac.org, navigate to the resources, webinars, find the webpage for this particular webinar, and there's a link to download the PDF of the slides directly from there. So you could follow along with those slides and the audio that you're listening to on your phone. For those who are dialed in or joining in through the AnyMeeting portal or platform, just wanted to quickly draw your attention to a couple buttons. At the top of your screen should be a little dialog box that is a place where you can submit questions. So at any time during this presentation, I would encourage you to click that, to enter a question and submit it. When we get to the end of the presentation, we'll go through those questions one at a time in the order that they were received. And so you can just simply submit that and we'll get to them later. There's a chat function, so I'll distinguish the chat feature, which will be on the left-hand panel of this of your screen. Distinguish that from the questions. We would really encourage you, if you want to submit a question, to do it through the little dialog icon that's located at the top of the screen if you're in the web portal of this. And then again, the flow of what we're going to do here, format, Ken's going to have the majority of the time for his presentation, and then the latter portion of this is we'll jump into the Q&A time. So I don't want to take up too much more time, so I will get ready to kick it over to Ken for an introduction for himself. One thing I did want to highlight here is not only is Ken going to give us a presentation, an overview, a somewhat quick overview of this content via presentation, but he's also written kind of a more documented report on this topic as well. And so if you're looking for documentation on this, a report to be published, that will be forthcoming. We are helping to get that published, and we'll direct everyone to that. We'll make sure we update the webinar webpage associated with it, perhaps even republish it on our website in its entirety, and or send out a link to the larger community of where they can find that document, either in DTIC or elsewhere. So just keep an eye out for that. I wanted to make you aware of that. And then final note, this is being recorded. So if you do have some technical difficulties, you get dropped out, just know that we'll be able to get this out to you and you can rewatch it at any time. So that was quite a lot, but without further ado, Ken, I will kick it over to you for the presentation.
Well, appreciate it. Thanks, Brian. Hello, everyone. My name is Ken Kwasniak, and I'm an applied physics experimentalist and researcher at Service Engineering, and I'm a contractor to the Army Research Laboratory. And one of my main tasks at the lab is to pretty much fabricate and assemble circuit boards for a whole assortment of equipment and other things. So I kind of made this whole overview here, small little tutorial to kind of guide people in the process. So if you want to go to the next slide. Here we have the agenda. I kind of broke it up into about 5 parts, just a little brief introduction and kind of a little setup on how I put together everything. Then I'll go into a little bit more about resource creation using CAD CAM software. And then I will then go into detail about how I designed a 2-layer PCB board from scratch. And then I'll discuss pretty much my findings from that. Next slide, please. So at the beginning, we'll go over the introduction. You can go to the next slide. So the Eagle CAD software is named Easily Applicable Graphical Layout Editor. And it's a eCAD tool and a CAM software. It's a computer-aided manufacturing software. And it helps the designer to take an idea, kind of put it on paper, and basically draw it out from a prototype to more controlled design. Now, PCBs are electrical circuits that are etched on assorted laminates and via conducting material such as copper that branches through various layers of insulating dielectric to form interconnected networks. Now, to the right, to the top right, we have a small little view of Eagle that kind of threw out a PCB with a board file there. You can see all the different kind of colors and connections. The middle picture there is pretty much like a schematic view, pretty much where you'll be doing all of your routing and tracing. At the bottom is a board picture. You will be routing and placing all your components and making the physical board. Next slide, please. So we'll look at a little bit of design phases here. So typically what I see here at the lab is we'll have an idea and we'll throw it on a breadboard. And once we kind of get that up and running, we kind of want to transition that to a little bit more sturdier design. Maybe it has better connectors. It can actually survive maybe out more range environments here and there. But essentially, we want a complete and finished product where we can fine tune everything. So that's where we use a PCB, which is all the way on the right. So main reason why we have a PCB, we're looking for quality, ease of assembly. We want some deterministic behavior from all our signals. It does look a lot better, more professional as it's packaged. And more importantly, we can conform to requirements. Next slide, please. So the big question is, what do I really need to make a PCB? I guess in theory, all you really would need is a pencil, some paper, an idea, and a really clever manufacturer. That's great, although this can be extremely expensive, difficult to track, and very time consuming. That's because not all manufacturers can guess what you need exactly, and they really don't know your requirements unless you write down every single detail. And I guess if you let them do that, you hope that they get it right. So that's where the Eagle eCAD CAM software comes into play. It pretty much can take your idea and you can make the necessary manufacturing files. So you can configure everything that you need to your own requirements. Next slide, please. So here we'll go up to the setup. In the top right, you'll see here I have a small little picture of my, that's okay, of my CD file that I used. You can go on the next slide. Thank you. So the next few slides here, I kind of throw out every single thing I used to design, test, and implement the procedure for this paper. So this whole section here kind of just goes over the small soldering tools that I use, some multimeters for testing the electrical circuit, some cleaning agents for, making sure that circuit's all brushed and cleaned up, and a programmer. Now, a lot of the stuff is way beyond the scope of this paper that I made, but in general, I kind of threw out all of my settings here. Next slide, please. Here we have our PCB components. So I know we're getting a little ahead of ourselves, but I just threw in every single thing that I knew that my PCB would contain, which I'll go over that in detail later. But just throwing that all, I think I got everything here from DigiKey. Next slide, please. Here, for the environment for the computer, I pretty much was using a Ubuntu computer, and I have a virtual box that's running like Windows 7. And from here, I was able to install my Eagle software as well as my programming software. And inside the Windows, I kind of configured my directories here. Main thing is making a bunch of folders, and then in Eagle, referencing those folders. Next slide, please. So the main window, when you install Eagle and you open it, you'll get this control panel. Now, this control panel here will house all your project files, especially everything that you throw into your directories. So in this section here, we're going to use this to create a new project and then add the relevant files that we'll need. Next slide, please. And just for a little heads up, there is a little bit of software conventions used here. When we open up Eagle and we go to either the schematic view or the board view, they'll have a ton of different colors depending on what layer you use. And here we can configure our own colors for certain layers or different symbols to help us kind of understand how we're building our circuit. And on the right here, pretty much on every single workspace file, either board or schematic, you'll have a toolbar here that has a huge ton of assortment of tools that range from everything from looking at different layers, looking at properties of every single element or wire you have there, to manipulating everything that you need. Next slide, please. The next big thing that we'll kind of look at is that in the Eagle control panel, there is a drop down in the menu for configuring your design files for your board. Or in this pictures here, I looked at the board editor, and there's a small little icon that's called on the bottom right that says DRC. And here we can set all the requirements that we need for our boards. So we can here discuss our layers, clearance, distances, sizes, restringing of the holes, shapes, supplies, masks, and some other miscellaneous requirements. Next slide. So in the first thing is, when you go in the DRC, is the layers. So here we can look exactly how our board will stack up. And they have this, and right in the middle, there's a setup with a type-in window. They have a certain way of how you can build your board. So they kind of give up an example down below on how to actually type up and build board and combined two layers together, also with adding vias or blind vias. So for instance, in this whole setup here, I'm only using a 2-layer board, nothing fancy. So hence why I'm using only these layers 1 through 16, and I'm tying them together. And you can get fancier if you really want to do other kinds of boards, but we'll probably explore that later. Next slide, please. The next step is then looking at our clearance. So we're looking at the minimum distance between kind of like 2 signal layers. So we can also specify this according to wires or pads or vias or SMDs. So it's important, I guess, we're not going to go into too big of a detail about circuit optimization and really making sure your traces are perfectly matched length and everything, or impedance matching. We're kind of just using the basic settings for everything right now. So next slide, please. Next is distance. For instance, if you have a component on one side, how close your signal layers can be right next to that, or how close your pads can be. Again, using the defaults. Next slide. The next is now your sizes of your width of your objects and the signal layers and your drill holes. So this can specify everything. I'm using the defaults for all this again. Next slide, please. The next thing is restringing, which is basically when you have your hole through your board, pretty much the copper ring, you're putting out, you're defining that. So again, I'm using all the defaults for this 2-layer board. Next slide, please. The other thing we can look at now is the shapes of all of our pads. Again, using the defaults here, I'm using as it is called out in the library. Next slide, please. I guess the third to last, we have masks. So that's the geometry of the thermal annulus symbols that are used in supply layers. We can get fancy here, making pretty cool stuff, but right now we're just using the defaults. Next slide, please. And next one is the dimensions, basically where we have our solder mask and where it stops. So we have our thermal annulus, and then we have our, for instance, our green mask layer is going to go over top. Here we're defining the distance between those two here. Again, using the default. Next slide. And finally, let's say you wanted to make sure you set everything in your boards a certain position. Here we can make sure it checks to certain grids, certain angles for parts, check fonts, and then it obviously checks restriction zones. For instance, if you don't want to have certain parts with, maybe you have parts with a certain amount of clearance, you want to make sure that are stay between 2 parts. You can have that here as well. Next slide. So now we're getting to the portion where we're going to create our resources. So in Eagle, for the board and the schematic editors, we'll have certain things that we'll be pulling from in order to populate our schematic or board. Next slide, please. So the first part, we'll have so a component, like let's say a chip, an IC. It'll have 3 main parts. One is a symbol, second is the package, and a device. That will all be kind of contained in the library. Now, these devices will contain your symbols and packages and assemble them such that when you want to open a library and look at a component, you'll be able to extract everything you need from that. Next slide, please. So now we'll look into creating the symbols. So you can see down here, down below to the bottom left, we will have our schematic workspace. And we'll use the tools on the left-hand side, for instance, the wire tool, to draw out our outline for our box. Now, we have to make sure that our line is in the correct layer. For instance, here, I think this we're in the symbol layer. And we want to follow a design scheme for this. For instance, we want to make sure everything's spaced a certain amount such that when you place it on the schematic, everything looks nice and even. So we can follow 2 conventions here. We can follow an ordered convention, which means when we look at the part, you'll have the pins going from counterclockwise pin 1 from the top left, all the way circling around to pin 8 on the top. For instance, this is an 8-pin IC. Or you can do it a functional way. Some people like to associate, for instance, if an IC has has 4 pins and all the ground lines are down below. Maybe you might just put all the ground pins down below, put your signals that are coming in to the left, and have your signals coming out and going to the right. So pretty much right here, we'll draw up how our symbol for a certain component looks like. Basically, we want to use our data sheet for that. So you want to find a component, look at the data sheet, and kind of map exactly how they have it. Next slide, please. Once you have the symbol completed, we can switch over to building our package. From this package here, we'll see that we're right now on the bottom left, we're defining our body of the object. Basically, it's a reference layer saying that this is the overall shape of the chip. And then from there, we'll associate certain holes, certain drills that we'll need in order to mount the component. And then we'll also probably add some restriction zones to help us obviously, when we're doing our design review check, make sure no components interfere with one another. So again, we'll be using our tools that are on the toolbar to the left. For instance, the info tool is used here to click on a pad, which in the center photo here, you can kind of see all the properties of the pad. You can change its shape. You can change a lot of aspects of that. And for instance, when we're drawing this package, we'll be doing everything in the so-called top layer. I understand that later down the road, we might want to add some components to a bottom layer of a board. That's something a little different. But when we are adding a component, I guess you can see in that middle screen there, there's something called mirror. That will put it on the back side of the board, the other side of the board. But for right now, model everything on the top layer, and we can worry about that later. Next slide, please. Then finally, now we're going to assemble both the symbol and package into what is called a device. So in the bottom left here, we're going to be adding our symbol. And then from our symbol in the middle picture, we are now going to add in our package and associate them. In the bottom right, we're going to connect the pins, the pinout, to formulate the device. We can get fancy here. I think there is a description tab, so we can throw in tables that represent different provisions of parts, maybe all the part information we're throwing there. I think in the end of these slides, I have an appendix on a little brief example on how to do that. And from here, after assembling the device, we pretty much have finished making our resources. Next slide, please. Oh. And then when we're completed our resources, and we throw them in the correct folder, we'll have, we can, for instance, look at our Eagle Libraries folder we've thrown, and then we can activate that. You want to make sure that this button here, that's circled in red, is green. Make sure that you're allowed to use that library for this project. Next slide, please. Now I'll go into the scratch how I actually made a two-layer PCB design, utilizing some of the resources that I created from scratch and some of the equipment that I had in the setup. So next slide, please. All right, here's the fun part. So now we have to think about what we really want to do. So I really just wanted to make a really small demo microcontroller board that kind of controls 3 LEDs. So just thinking out loud real quick, I said, well, what kind of dimensions do I want? I was doing 1.5 inch, 1.5 inch, and I guess the standard board thickness is, 63 mils, sure. I prefer to use lead-free components. FR4 is a generic material. Sure, I'll use that for my electric. Then what kind of board color do I want? I really don't care. Green's usually nice, with 1 ounce of copper for the weight. And I like to have white text over that. And maybe I'll have text on the bottom and the top of the board, but primarily I just put it on top of the board. Might save me on some costs. And then all the holes I have, let's say I want to make them plated. Maybe I want to ground my ground layer to my chassis. So on the right side here, I kind of threw out a small diagram on the steps you kind of have to follow, all the way get through from setting up your file structure all the way to sending files to your manufacturer. So we'll step through these. First, you can go to the next slide, please. So step 1 is the file structure. And in the Windows environment, I just opened up a file explorer and I just started creating my file structure here. So I just made a libraries folder and I made a projects folder. Now your projects folder it should house like all your schematics, your boards, reference files, fabrication files, notes. And in this project folder, you might break them out into different subfolders to kind of help you collect and organize everything. I do this so down the road that we can easily package our device all into one project and we can label it accordingly. Next slide, please. So pretty much when we have our files in our Windows Explorer, we have to make sure that Eagle understands where they're at. So in the control panel in Eagle, I pretty much go to options and directories and basically throw in every single one of my directories that I want this thing to refer to. Next slide, please. And then once I had that done, it looks like this is a duplicate slide. This might be an old slide deck, but it's okay. We'll basically go to the projects folder, we'll right-click on that, and we'll tell it, create a new project. And from there, we'll have a little red folder that pop up. The green little LED that's right next to the folder will pop on, saying that the project is active, and we can go on and start using, creating materials for our project. Next slide, please. So we will create a new schematic. I guess we have an idea of what we wanted. We kind of define that, but now we'll actually create the material in the eCAD control panel and start formulating. Maybe start researching some components that we want to use. Then we'll now kind of make a systems diagram of kind of what we want to use. For instance, in the bottom here, I have a battery or an external power supply that will giving power to a certain section of the board, and that power will feed to the microcontroller and maybe to the programming components that I need. And then the microcontroller then will have to control the LEDs. So at least I'll have an idea on the bill of materials that I'll have, and I can now go to the eCAD libraries and activate the libraries that I need. For instance, in the middle picture here on the top, I use all the libraries. Maybe there's a component in there that I would like to use. And from there, I'll also use a frame that they have, just to kind of give a good generic outline for these for a schematic. So next slide. Now in designing the actual schematic. So we'll be taking the components that we made earlier, some of the resources, and adding them into the design. There's a tool on the left-hand side that just allows you to add your components. So on the bottom left, we'll have all of our libraries. And from in there, we can search through them, pick our certain component that we have created, or our device that we created. Now, sometimes eCAD won't have all of our components that we want. So we'll have to either create our own, like we did before, or we can import. Now, if you look at the center picture, kind of the center one to the left, I've imported a switch, and obviously that does not conform to our schematic scheme. So what we had to do is that we had to take that symbol in the device when we create a variant. We just changed the schematic a little bit to conform to what we want and to match our schematic. So there's many different things you can do. I said use existing libraries, import libraries, modify existing libraries, or just create only one from scratch. Next slide, please. All right, so then we'll kind of look at, after we started assembling our schematic, now we actually want to move things around and actually map the nets and connections. So here we have a general idea. I said from our systems diagram, we kind of thought it before. We have power on the top left, kind of going straight into the microcontroller. It's that big guy in the center. And then from there, we'll start branching out where the LEDs go, where the programming headers and everything go. Now, when you're mapping these connections and nets, you probably can also use what's called as a name tool. So for instance, we can name the signal that's coming from the battery. We can call that V battery. So that way, when we're doing our board, we can also find that signal pretty easily. And here we can also add in some notes. For instance, I put in some plated through holes here that will use vias through the board to the job for us. And I put some notes above a programming header to make sure that that's exactly what we're using that header for. So here we can also make a lot of notes on here, maybe what we expect the behavior of the circuit to do. For instance, how much voltage we're expecting here, or how much current is being pulled through. Next slide, please. And pretty much once we have outlined all of our components and we throw in all of our notes, we'll run something that's called an ERC, which is an electrical review check. Here, it will look at all the different pin types assignments, missing connections, unintended grounds, basically your connection diagram, and it'll throw up errors. For instance, in this screen here, I kind of made a small cabling diagram on the top of one of my programming headers, basically for what the programming cable would look like, and it's throwing a bunch of errors saying, hey, you're seeing a bunch of these wires, and they're not connected to anything. Well, I could have, when I drew out the wires, I could have put them on a document layer, so it wouldn't throw in this error, but I didn't really do that at the time. But I also know that these wires are not connected to anything, so I can simply ignore or approve this error. Next slide, please. Once we have completed our whole layout, we approved all of our errors and checked our circuit and make sure all the pins are associated to what there should be, we'll move to create a new board layout. So in the schematic workspace, there's a button that you can switch between the board and the schematic, or we can go into our PCB project file and create a new board file that way. Next slide, please. And from here, once we get our board workspace, the first thing I do is I go to the DRC. Again, you would want to configure all your details, for instance, your layers, your clearance, distances, etc. Make sure that we have the exact requirements we want. Next slide, please. So when we opened up our board, we're done with our DRC, you're going to see a bunch of your components kind of thrown all on one side. So what we'll do is we'll use a bunch of the tools to move or reorient components on the board, and then might resize the board as well to make sure we fit everything to kind of how we wanted it. On the bottom left picture here is kind of like the ideal situation I had. I still had my 1.5 by 1.5 inch board. I was able to fit everything in there. I was able to add my vias, add all my components. I think it was looking pretty good. So one thing that I had to use pretty often, because I mean there's a lot of parts and a lot of wires going everywhere, is the display tool. So here I flip through and look at different layers here, so I can see if anything's overlapping, or obviously get a better view of what I want to implement on my top layer or what I want to use on my bottom layer. Next slide, please. After I kind of positioned all my components, I wanted to create a copper region for the top and the bottom. So I use another tool. I use a polygon tool to map over a whole entire top layer, and then I use the info tool to make sure that I change that whole entire polygon, which is a square over top of everything, into the solid fill layer. And also I have to make sure that these are on their correct layer. For instance, there's a top and bottom layer. Next slide, please. Afterwards, you can use what's called a rat's nest tool on the left-hand side in the board editor. The picture on the right will kind of show, once you hit the rat's nest tool, it'll show the combination of the top and bottom layers as a big square color. For instance, the top layer is red, the bottom layer is blue. So you kind of see that little magenta kind of like color. Now, obviously, when you're adding in your traces, you're going to basically put your signals in through your whole top layers. So here we can look that we're now tracing everything, and while we're, for instance, using the wire tool, we can switch between different layers to create, going from the top layer to the bottom layer, and we'll use a via to join those that signal. So once you have completed routing your layers to everything, we can use the rat's nest tool again. It'll kind of redo that your copper layer to incorporate your signals and your traces. So the figure on the right, you kind of see I use the auto router tool here to help. It's a very simple board. The auto routers may not be the best thing to use, obviously, because you can probably optimize your design a whole lot better. It's basically writing out things by hand because it doesn't know if you're using it for a USB line or anything else. But yeah. So we can go to the next slide and kind of look at the auto router properties here. We have the top layer and bottom layer is the only two things I'm using, and these the directions here, basically the drop-down box kind of tells the auto router how to actually form these traces. So I'm not going into anything fancy. I'm not worrying about any buses or routes or optimizing anything. I'm just worrying about maybe I can put my traces on a grid. That's what the routing grid is, 50 here, and via shapes, I'm gonna put them all as round. So I want to have the auto router look at all my signals as if I didn't route anything previously, and I want to have everything 45 degrees, bottom left, the top right, and I'm going to go ahead and I guess have that work for me. It generated a circuit. It was pretty decent. You could obviously do some of the circuit yourself and trace it, and then use the auto router to fill in the easy stuff. Maybe you have a bunch of straight lines, a bunch of resistors to another power pin or something like that. But that's probably what use of the auto route would be. Next slide, please. So once we have all our traces routed, then I kind of look at putting in a silk screen and everything. Now, some of your components, when you imported, for instance, from a third party, they might not have their silk screen components, they might have a nice, wild, long name. So, for instance, on the bottom left, that you see MCP1702, that was along of the linear regulator, and that's a little too long, and I don't want that name on my silk screen. So it could be possible that you might have to go back into your components and rename some of these, rename the name or rename the value for all the components. Or obviously you can hide it altogether. Mainly I keep my name on all the components. For instance, instead of NCP, it would just say IC1. And then when I'm doing my assembly or my bill of materials, I'll know that IC1 is related to my regulator. Next slide, please. So once we have completed our silk screen, then we'll use our DRC to actually now perform error checking. So we've already set our requirements in all of our tabs, but now we're actually going to use the check button. I think that's highlighted in the first picture on top right. And here we'll look at every single one of our components with our requirements we set, see if there's any errors. I ran into this one error here on the bottom right, is that, the picture on the bottom right, is that I have my small battery, I guess the silk screen that's on the bottom side. It's interfering with a pin that I have obviously on the bottom side for a power plug. Now, there's two things we could do. I mean, we could change our board requirements, but that seems to be that would kind of be a pain. So I think the easiest way to do is create a variant symbol and just change my silk screen from my outline to make it a lot smaller. So in the bottom center, you kind of see two little concentric circles. I just changed the size of my silk screen, and that actually solved the problem. Next slide. So once you've approved all your errors, everything looks good. Next thing you can do is now start creating your fabrication files. So we will be using two main things. We'll be using some user language programs, as are ULPs that Eagle has, and also Eagle's CAM processor. Next slide. So the first one is the user language programs. We'll be using what's called the drill CFG at ULP, and it will create a tool list for you. That's the DRL, that's the drill list. It'll tell you all the different types of drills that you have in your PCB. Now, here we can do some slight optimization for our circuit. For instance, if we have two drill sizes that are extremely close to one another, we could rename those drills to be the same drill to save on tool changes and time. Might save us some cost down the road. But once that's done, you can hit OK, and we can go to the next slide. The next, we'll use the CAM processor to use for Acceleron data, Acceleron.cam. And the output right here is giving us a drill dimensions and our drill information. And we can run this script here, give us our outputs, and then we can go on to our next step. So next slide, please. We use the CAM processor again to create our Gerber files. So here we're using our gerb274x.cam. And here, when you go to load up your own CAM file, I guess load up the defaults in here, it won't have all these tabs. I kind of deleted the defaults they had for here, and I created all my own tabs. Now, for instance, on the right side here, I just started with the top silk screen, and I basically highlighted my two layers that I want to be placed on for my Gerber file for the top layer, top silk screen. And I did the same thing following for my top stop, top copper, and bottom copper, etc., which you will see in the subsequent lines. Next slide, please. So here we will have our output for our top stop. Next slide. Here we'll have for our top copper where all of our traces are. I think I used the pads, vias, and top layers. Next slide. Here we'll have our bottom layers for our bottom copper. Next slide. Then I go to our bottom stop. That's just B stop. Next slide. Then I'll worry about placing our silk screen on the bottom layer. That's the B place for our B silk. Next stop, or next slide. And then we have our drill dimensions I did for a board outline. Next slide. And then finally our .ddrl. This is all of our drill holes and our drills and holes for the board. Next slide. Now we can go to our description tab here, and again in HTML format we can throw in kind of exactly every single thing that we'll have for our layers for our Gerber information. And then when we're done this, we can use the button that says process all, and it'll create all the files that we need. Now, I will note that there is a output box, and you will see it, a Gerber 247. We'll make sure when we create, before we create these files, we'll rename the correct file in there and place it in its right respective location in our file structure. And once we hit process all the files there will then dump into our folders. Next slide. One big thing I also like to do is like to create like a text file. You can do that through the equal control panel, or in general, just create a regular text file. And I'll throw in a ton of contact information, how to get a hold of me, software I use to generate all this, some tracing history, maybe some versioning control. Then I'll start outlining some requirements for my boards. Then I'll, again, reiterate everything I want for my Gerber files. Basically, what each file is. My DRL file is a drill file. My DRD is a acceleron.cam file, so drill location information. And I'll go over all those files. So when the manufacturer receives this project, he can open this README file and really get all the information he or she needs. Next slide. And this is probably one of the easiest parts, considering that we made a nice little file structure and layer. We really just have to right-click on our folder in the Windows File Explorer and compress the file, kind of make sure we package everything into one folder, and then we do some version control. Maybe we can give it a version number at the end or give it some kind of serial number. Next slide, please. And then once that's done, we pretty much can send our files to the manufacturer. But before you really want to send everything to the manufacturer, I always say to everyone, just make sure you read their license agreements, make sure you understand what you're sending and who you're sending to. And sometimes when you're using the auto quote tools, auto generation, they might be really fast online, but they might not interpret your files correctly. For instance, when we create our own layers for our Gerbers, those names might not link up to exactly what the manufacturer is looking for. So you might have to do an extra step here and there to correct that. Obviously, the best answer is always call a representative of the company and discuss your project. Yeah, it will probably introduce another person in the loop, and that might increase your time. But if you really want to drill down and get something correct, it's best to talk to somebody. Next slide, please. So now I'll go over a brief discussion on using everything I did earlier to actually create this board. Next slide. So in general, we went from a symbol, we went to a package, then we went to a device and compiled the symbol and package. And from here, we use these devices in our schematic. And when we finish our schematic, we're able to produce a board file from that. And from that board file, then we're able to make our manufacturing files, our CAM files. Next slide. So quick discussion. So I used OshPark to create this board here. And funny enough, I didn't really have to create all those Gerber files. I actually just needed the Eagle project file. I just clicked and dragged through my file in there. Now, they're pretty quick in turnaround time. That's one of the reasons why I chose them, and they were fairly inexpensive. But I will note they were pretty limited on board styles, and there was no live reconfiguration tools. For instance, there was no real viewer to help me correct the hole size if I need to change anything. I had to go back into my Eagle project and fix everything that way. Next slide, please. All right, so once I received the board, inspected it, I took a multimeter, checked all the connections, everything looks like it connected to where it should. So what I want to do is just populate the board with some readily available components to make sure it at least powers on correctly. It's a very simple board. I mean, you have power in, which goes to regular, which goes to the microcontroller. So I just threw on a regulator, threw on an LED, powered it on, and everything looks like it worked. So, okay, now I'll actually populate the whole entire board and actually program it. So hooking everything up with kind of said stuff I had around the lab, I was able to hook it up, program it perfectly fine, and test the LED functionality. I do have its code also in the appendix if you want to refer to that. It's a pretty simple standard code. And then I pretty much cleaned up the board, made it look nice with cleaned up the board from all the solder connections I had, and surprisingly enough, it all worked out very well. And I think that's the end of it. If you want to go to the next slide. Yes, then I have my appendix for everything. So just really quick, I'm not going to go through all of this. Yeah, you can just jump through it. Just basic code and how to actually configure and program the whole entire thing. I even threw in notes on what everything meant, references to where to find the data in the data sheet. And then I go to this appendix here where I kind of go over the HTML format on if you want to put a description inside Eagle on how to do this. And I think that's, yep, and just a bibliography on all my references for all my components, my parts, and hardware. And I think that's it. Thank you.
All right. Thank you very much, Ken. That was great. Very good presentation. I appreciate that. Very well practiced too. Time-wise, it was great. Despite having 69 slides, you were quite efficient with them all. So that was great. Thank you.
Yeah, I practiced once or twice. Yeah.
Very good. Well, we did have one question come in. I do want to encourage everybody else who's still sticking with us here. If you have a question, little dialog box at the top, you can enter it in there. So I'll at least kick it off with this question, and then we'll save a little bit of time for any other might come in. All right. So if you should be able to see this question as well, Cam, but let me just read it for those who are on the phone. DigiKey has say KiCad for footprint of parts. Can they be ported over to Eagle?
I have looked at KiCad before. I don't think it's a direct import for this version of Eagle that I'm using, but I think obviously the most recent version probably does have imports. And I know that DigiKey also has, I think they use Ultra Librarian. They also have footprints that are in Eagle format as well as KiCad. So they should be from the same site. You should be able to find Eagle component as well.
Very good. Thanks. Let's stick around for a few more moments here if anyone else wants to submit a question. I do apologize if you are on a phone. There's no way to submit a question or ask a question. We'd have to unmute everybody, and this software doesn't give us the opportunity to unmute everyone on the phone. But again, if you are in the web portal version of this, you can just kind of click the little button, type it in, and enter it that way. We'll just kind of stick it out for a few seconds more to see if there's any other questions submitted before we close out.
Sure.
All right. Well, I won't hold us out in silence for forever here. I think we can kind of call it. If there are any other questions, I mentioned in the beginning, as an organization, DSIAC helps. We help people find information they need on any projects they might be working on. So Ken's one of the folks that is working for the company that helps run DSIAC. So he's kind of on our Rolodex of sorts for any questions. So if you do have a question, please contact myself, DSIAC alias, or of course Ken himself with anything pertaining to this topic or this presentation in particular. And other than that, we will be recording this, send out a brief survey that'll come out after this, and just appreciate everyone joining in on this webinar. And Ken, thank you very much for delivering it to us.
Sure. Thank you, everyone. I appreciate the time to actually present this.
All right. Thank you much.